Alright, today what we're going to work on is how to solve a system of equations with the elimination method. We've done graphing and substitution, and I kind of cheated ahead of time, and feel free to pause this if you need to, but I wrote this down already. In general, what I would recommend that you do to solve a system of equations if you're using the elimination method. First of all, this is really good for if your two equations are in standard form, or if it would be easy to get them in standard form. So a lot of times this is the best method for that. What you want to do is you want to create, or maybe it just already exists that way in the problem, but you want to try to have opposite coefficients on the same variable. I just did like a little example. I just did negative 3x and x. That's what you'd want it to look like when I say opposites. I just mean one's positive and one's negative. And then you just go ahead and add the two lines in the system together, and that will eliminate that variable, leaving you with the other variable that you're trying to solve for. So just a couple of examples to go through. This first one I have, what I would just do with this first one, I already have the same number of 4 on both of the x variables there, but I would just run a negative through that second equation, or you could do it with the first one. I'm just going to do it with the second one real quick. That will just multiply everybody by -1, which is going to create an equivalent equation, as long as I do the same thing to everything, and that creates opposites on my variable of x. Then when I add 4 and -4, that adds up to 0, which is what eliminates that. 1y minus 2y, we'd have -y, 0 plus a -20 would be -20, and then the two negatives there are going to cancel out, so y will be 20. Now, once you get that, don't forget, you want to plug it back in. I'm just going to plug it into the first equation there for y. Neither one of them is easier than the other a lot of time when you're working on elimination. If I subtract the 20 from both sides and then I divide by 4, that'll give me my x value of -5. And just remember, you want both variables because you're trying to tell me where would these two lines intersect on a graph, and this particular one happens to be a nice point, which is -520. So that first one was kind of set up nicely for us. So the second one, I don't see the same number on the x's or the y's. So what you want to ask yourself is, okay, would it be easy for me to multiply one of the variables by something to make it an opposite to the other equation? So nothing you're multiplying 2 by to get 7 without working with fractions. So let's not do that. 5 and 15 though, those are factors. So if I were to take 5 and multiply it by 3, that would be 15. I'm just going to run a negative through here. That way it'll be -15, and then we can eliminate the y's there. So I'm just going to copy that top line exactly as it appears. The bottom line, everybody gets multiplied by -3. Just run that -3 through. This will turn into positive 21x. This will be -15y, which is what we want because we want opposites on that same variable, and then we'll be able to eliminate it. And -3 times -17 is going to give you positive 51. And we're just going to add those two up to 0. This is going to be 19x. And then I'm just going to take -32 plus 51, and we're going to actually get 19. So x there would just be 1. And again, you can plug this back into either one of the original equations, or you can plug it into one of the equations you created. In this particular case, I'm just going to use that first equation real quick. It doesn't really matter. I wouldn't say any of these are easier than the others here. So if I take -2 times 1, that's just -2. And I'm going to add that over here. So I'm going to get 15y. That'll be equal to -30. And then y is going to end up being -2. So don't forget, get both of those variables because you only have half the answer if you only solve for one of the variables. Okay. And then down here at the bottom, so I've got a situation where I might have to multiply both equations, because 2 is not getting multiplied by anything to make it 3 that's not a fraction. Same thing with 4 and 5. If that's the case, you can totally choose the variable that you want to go after. I'm just going to go after the first variable that appears, and that's going to be x. So what I'm going to do, I'm going to multiply the top line by 3, and I'm going to multiply the bottom line by 2. That'll make both of my x's 6. But what I do want to do here, I want to introduce a negative. I'll just put it on the second equation. It really doesn't matter. But make one of them negative so you have opposites. So I'm going to run a 3 through the top. So that's going to end up giving me 6x plus 12y equals negative 12. And I'm going to run a negative 2 through the bottom. So that's going to give me negative 6x minus 10y. And then here, negative times a negative, this is going to turn into 6. That allows me to eliminate the x's when they're opposites. They add up to 0. 12y minus 10y is going to give you 2y's. Negative 12 and 6 is going to give you negative 6. So then y there is just going to be negative 3. And then again, it doesn't really matter which equation you plug it back into. I'm just going to put it in that very first equation. Make sure you do plug in for the correct variable. We found y first there, so I'm going to plug that into that first equation for y. You can get 2x minus 12 equals negative 4. I'm going to add that 12, so I'm going to end up with 8 over here, and divide by 2, so x will be 4. So I'm looking for that intersection point, if we were to have graphed those, would be 4, negative 3. All right, and the one at the bottom here, this is kind of nasty with these fractions. What I might recommend here, let me just start this out. I'm just going to multiply everybody in that first equation real quick by 4. I'm just going to create a new system here. I'm trying to get rid of the fraction so I don't have to worry about that. So that's why I chose 4, because that'll get rid of that. So this will become 4x. If I multiply that right here, this would just become minus y. And if I multiply 4 by negative 1, that'll be negative 4. So I'm not changing anything here in terms of what the equation means. I'm just trying to make it a little bit easier to work with by getting rid of that fraction. And I'm going to do the same thing to the bottom here. And then we'll see what we're working with without the fractions. Now, I would argue to you here, this is a little bit trickier, this one on the bottom. But I'm trying to find a number all 3 of those would go into, so I would recommend 15 there. And I'm just going to write this underneath so you guys can see this. So it'd be negative 15x over 5, 15y over 15, and then 15 over 3. So I'm just going to write it up here underneath the line. That first term would just be negative 3x plus y, and then 15 divided by 3 is 5. And actually, you guys can see, hopefully, when I got rid of those fractions, that actually gave me a system where the y variables were already opposites. So we can actually just eliminate right then and there. So this is just going to give me x equals, let's see, 1. And then here's my recommendation to you here. I would not plug this back into one of those original equations in the system because I got all the fractions. I would just use one of the equations we created. So let me just go ahead and use that first one. So x is going to be 1 here. And I'm going to figure out what y is. So this would be 4 minus y equals, negative 4. If I subtract 4 there from both sides, I'm going to get negative y equals negative 8. So then y will be 8. So it looks kind of complicated, but once I cleared the fractions, that actually turned out to not be too bad of a system. And the intersection point there would be 1, 8. All right. Now on the back, when we have been solving these linear systems, you either had one answer like we did for all the questions on the front, or we had those other 2 possibilities. We could have parallel lines, which would be no solution, or infinitely many solutions, which means the 2 equations in the system were the same line. So not always obvious when you grab a problem, but just want to show you what that might look like in a situation where you're using elimination. So here's this first one. So maybe I'm looking and I'm going, oh, it would be really easy to eliminate the x's, I could just take that top line and multiply it by 2 because -3 would turn into, I don't even have to introduce a negative. I'm just going to run a 2 through that top line and write it right underneath the second equation. What happens when I do that, though, is actually that makes the y's opposites as well. 2 times 6 there is going to end up being 12. So I'm focusing, I took that first line, multiplied it by 2, I just wrote it right underneath here. The x's and the y's eliminate, but what you got to remember is you're left with something there. I have a 0 there, right? Because it doesn't just disappear everything, it's just becomes 0. And then I add the 0 and 12, so I get 12. Right, so if both variables eliminate, and you're looking at that and you're going, I don't think so, 0 is not equal to 12, right? So this is going to indicate if it's not true, it's no solution. It means these two lines were parallel, but no solution would be my answer. Okay, now similar, I'm looking at this and going, oh my gosh, if I just took that top line and multiplied it by 2, that would make the x's opposites. I don't even need a negative. So if I run a 2 through that top line, it'd be -4x plus 3y, and then 2 times 13 is 26. And then maybe I wasn't paying attention, or maybe I saw it, but that, oh, fail. Sorry, I forgot to actually multiply that by 2. Sorry, 2 times 3 is 6. What happens though, these are opposites, these are also opposites, and -26 and 26. So 0 equals 0, and I know this is probably not cool to say or whatever, but this kind of to me like reminds me a little bit of an infinity symbol. So 0 equals 0 is true. If you get an elimination situation where both are the same line, you will end up with 0 equals 0. You're not going to end up with something like 5 equals 5 or anything like that. It will be 0, like looks like 0 equals 0, which I think looks like an infinity symbol. So this is your infinite solutions, and what it means is, even though it might not have been obvious to me, those two equations actually represent the same line. They're just written in a different format. All right, and then we got a couple word problems down here. So Mike has a jar of coins in his kitchen, dimes and quarters, 42 coins. Okay, here is the tricky part of this. Everybody wants to attach value to the coins all the time. If I just have 42 coins, nothing to do with their monetary value, I'm going to let D be the number of dimes and Q be the number of quarters. Okay, so here's my two equations. Money goes with money. So a dime is 10 cents and a quarter is 25 cents. So every dime I'm going to put 0.10 in front of it, every quarter 0.25. Money goes with money, so put that with the $6.45. Now, the other equation has nothing to do with the value of the money, how much it's worth or anything like that. It just says 42 coins. So my other equation, which I'm going to write over here, whoops, I keep thinking we have nickels, we don't. But just number of dimes plus the number of quarters is equal to the number of coins, which is 42. Now, easy options here, actually. If you really wanted to use substitution, you could quickly get one of these variables alone, like I could subtract the dimes or I could subtract the quarters from 42 and substitute. But since we're doing elimination today, what I'm going to do, I'm just going to run a -0.10 through that equation there, because our coefficients are just 1, so it's easy to do that part. And then this would just be $4.20 is what it would kind of look like. I'm going to eliminate my dimes there. This would be 0.15Q, and then I just got to do a little subtraction here. I'm going to take 645 and I'm going to subtract 420, and we're going to get 225. Now remember, I should not get a nasty number for any of these coin questions. It should be a whole number. So if you take that and you divide that by 0.15, you're actually going to get 15 quarters. Now in this case, I would tell you it's probably a little easier to plug it right back into that one and just take 42 minus 15 to get your number of dimes, which is 27. Very easy to plug these back in and check if you want to make sure they make your equations true. All right, and I got one more. It says Hope went to the store. She bought 5 apples, 3 bananas for $6.50. Grace went to the same store, bought 10 apples and 7 bananas for $13.75. Write and solve a system of equations to determine the cost for just 1 apple, 1 banana. Okay, so I'm just going to be super creative and let A stand for apple and B stand for banana. And so Hope gets 5 apples and 3 bananas. So I'm just going to say 5A plus 3B. And if we add those up, it's going to be $6.50. Then it says Grace goes to the store. She gets 10 apples and 7 bananas. And her total is $13.75. Put those guys together. And then if I want to use elimination here, what I might just do is say, hey, be super easy for me to match the apples up. I got 5 and 10 here, so I'm just going to run a -2 through that. So I'm going to just write it right underneath to save a little bit of space. So that would turn into -10 times my apples. -2 times 3 is going to give me -6, and then -2 times 650 is going to give me 13. And I'm just writing it like that so it's easier to subtract. This will just give me B, and 1375, whoops, I didn't put my negative fail, is just going to give me 75. So in that case, all the bananas are 75 cents. Now I got to figure out my apple price, so I don't know the apples. I'm just using that first equation. I do know the bananas now are 75 cents, and this is 650. So then I'm just solving that equation. If I take 3 times 0.75, I'm going to get 225, 650, and we're going to take 650 minus 225, whoop, and it's okay for these to not be perfect numbers because this is the cost, so every banana would cost 75 cents is what that's saying. Anyway, so I get 5A, 425, and I'm just going to divide both sides by 5 there real quick. And so each apple is then 85 cents. All right, and that's all for the elimination.